Let's review for exam 1. This is not a complete review. All this is just reminding ourselves of what we've done. A quick reminder in 17 minutes or so of what we've done. Chapter 1. Chapter 1 was mostly reviewing pre-calculus, right? We had a bunch of functions, a bunch of function types. We had linear functions. So that involved the different forms of the equation of a line, point slope form, slope intercept form. Of course, that also means you should be able to graph linear functions, plotting points, knowing the slope, knowing the intercept. But it also is some real life interpretations of the slope as a rate of change of y with respect to x. And what does that mean? It's telling you how fast y changes as x changes. The y-intercept sometimes has real-life interpretations. That's the value of y when x is 0, or when t is 0, if t is the independent variable. Solving problems, graphing, those kinds of things showed up in there. We also talked about function notation, understanding function notation. Domain and range showed up a little bit. Proportionality showed up. Section 1.2 jumped to exponential functions, actually. Before talking about other kinds of functions like, say, quadratics or cubics. I think the reason that they jump to exponential functions in the book is because linear functions and exponential functions are, to tell you the truth, the most widely used in applications. Linear functions are nice and straight, simple, slope is constant, rate of change is constant. Exponential functions are not straight. Exponential growth looks like this. Exponential decay looks like this. But they are, in general, more commonly used in many modeling situations than, say, quadratics. Quadratics do have their applications, the most common of which is free fall. But in general, exponential functions have more applications to other situations like, well, population growth, radioactive decay, money growth in a bank account. So finance, those are some of the more common applications of exponential functions. And they don't have a constant slope. They don't have a constant rate of change, but they do have a constant relative rate of change. If you put that word relative in there, that means percent. The word relative is essentially synonymous with percent. The relative rate of change, the percent rate of change, is constant. And in particular, if you've got a function, say, like this, 1.2 to the t power, say, as an example, that's the same as 1 plus 0.2 to the t power. That's a constant relative rate of growth of 20% per unit time. The 0.2 can get converted to a 20% relative rate of growth per unit time. And that's a constant relative rate of growth. The percent amount, the percent change each unit that t increases stays constant. Not the actual amount that y changes, but the percent change in y. 20% per unit increase in t. With exponential decay, like 0.8 to the t power, that would be a 20% rate of decay per unit time, because 0.8 is 1 minus 0.2. These also can be converted to the E form, where in this case, the K would be positive, and in this case, the K would be negative. You'd have to use logarithms to actually solve for K. We talked about logarithms, though not until section 1.4. Essentially, if you've got a 1 plus r to the t power equaling e to the k t, which is e to the k to the t, that is equivalent to saying 1 plus r, oops, 1 plus r equals e to the k, which is equivalent to saying k is natural log of 1 plus r. Now, we didn't always call the base of the exponential function 1 plus r. I think I tended to call it b. This could be your b. I think the book used the letter a, at least in some circumstances there. It doesn't matter what letter you use. What matters is the idea. I've emphasized that a lot. In section 1.3, we moved on to transformations of functions and inverses. Transformations include, your horizontal translations, your vertical translations. Those are the easiest kinds. But also vertical stretches or compressions, or horizontal stretches and compressions. Those get a little trickier, especially the horizontal ones. And reflections across the axis by multiplying your function by a -1. And combinations of those things. And inverse functions. When your graph was 1-to-1, it passes the horizontal line test. No horizontal line goes through it more than once. You could solve for the inverse function by solving for x in terms of y when it's invertible. And then if you swap the y and the x in the round and graph them on the same set of axes, you got the symmetry property with respect to the dashed line y equals x. But remember, if your variables mean something, that's not a good idea to do. It's not a good idea to swap them. If the variables mean something in a real life application, if you swap them, you're changing the meaning. And that's a bad thing to do, and typically because the letter used often is relevant. Like if t is time and p is population, population is a function of time, and you solve for t as a function of p, you don't want to change the p and the t around because it changes the meaning. And as far as the graph goes, you'd want to make a new graph with a new set of axes where you've swapped the labeling of the axes is what you'd want to do. Quadratic functions also showed up. And so that includes being able to factor quadratics when they are relatively easy to factor, at least, using the quadratic formula if necessary, completing the square if necessary. And that helps you understand the graph of the quadratic in terms of transformations, because it helps you understand where the vertex is. Vertex form, you remember that? Just trying to help you remember things here. These are all things that we talked about in our very rapid review of pre-calculus. Section 4 was about logarithms as inverse functions of exponentials. If f of x equals b to the x, then the inverse function is log base b of x. For us, the purpose of the logarithms is to solve exponential equations. You should be able to do that, usually using base e, the natural log, ln. Can use base 10, the common logarithm, log, if you want. Either one is okay to use to solve an exponential equation. There's the properties of logs. The log of a product is the sum of the logs, for example, and we proved that in class. There are a couple other properties you should be able to prove, so you'll want to practice that for the exam. It's not something, if you don't practice it, you won't know how to do it in the exam. Can you just put the proof on your note card? Well, yeah, but then that's kind of filling up your note card and you're kind of missing the point. You want to understand. You can watch the video that I shared where I did that. It was lecture, I don't know, lecture 4 maybe. If you can search through your email for that. You could also go onto the Moodle announcements and search for it back second week of class, third week of class, somewhere in there. Then we went on to trig functions after that. I think our book's philosophy is it's sort of going in order with these things in terms of usefulness, linear functions being most useful, exponential functions being next most useful, transformations, etc. The polynomials and rational functions you're sort of thinking as being the least useful. Not that they're not useful, it's just more commonly people have applications with these things. Trig functions, mostly sine and cosines. And the most important kind of thing to be able to do is you got a sinusoidal graph to find a formula for that, thinking in terms of amplitude and vertical shift and period. There's also tricky problems with phase shift. I won't give you an extra tricky one where you have to do some horizontal shift. Those are just a little too tricky. But dealing with the period and the amplitude and the vertical shift is something you should be able to do. And solving trig equations with inverse cosine or inverse sine, and thinking about the unit circle, maybe to find other solutions as well by maybe adding 2 pi to your answer or something like that. Using the fact that cos squared t plus sine squared t equals 1 came up as well sometimes to solve for a sine when you know a cosine. The most important kinds of applications. We did talk about tangent and inverse tangent as well, and the graph of inverse tangent and using inverse tangent. Yeah, that's something you should be able to do. Then we got into polynomials, rational functions. I'm just going to group a bunch of things together here. Limits, continuity. These are the last few sections of chapter 1, the last 3 or 4 sections was on all those topics. And I sort of tried to approach them all at once. Common kinds of problems you should be able to do would be like, if you got a graph that looks like it's the graph of a polynomial, you should be able to find a formula. When you know the intercepts, doesn't mean you need to simplify the formula. Should be able to graph rational functions to the degree that you can find intercepts and find asymptotes. Sometimes you got to factor and cancel first to deal with removable discontinuities to help you find limits. Understanding when you've got a continuous functions. Polynomials are continuous everywhere. Rational functions are continuous wherever they're defined, as long as you're not dividing by 0. But that includes original values of x before cancellation. And when that happens, you either, again, have a vertical asymptote if it did not cancel with something on the top, or possibly a hole in the graph if it did cancel with something on the top. We talked about all this before. The relationship between limits and continuity. Continuity, you can draw the graph without picking up your writing utensil. Ways functions can be discontinuous is removable discontinuities, jump discontinuities, vertical asymptotes, but also the infinite oscillations, the strange examples. Being able to approach limits graphically, symbolically, and knowing their properties. Being able to do various limit calculations. The definition of the derivative comes up as the limit of a difference quotient like we talked about today. Where does that come from? It comes from saying I'd like to be able to find a slope of a tangent line when it exists as a limit of slopes of secant lines to the graph, and you should understand then not only how to calculate those limits, but what it means in real life applications as a rate of change, including in physics. But also there were some other applications like population growth. Sometimes you have to rely on your technology to approximate the limit. Sometimes you can do it symbolically. You should be able to graph a derivative if you've got the graph of the original function. Graph the second derivative, approximately at least. We're not looking for perfection, but we're looking for decent. Looking where the slopes are positive, negative, and 0. Looking for the concavity, where is it concave up, concave down, where the inflection points where it changes concavity. and then differentiability. So that's a very, very quick 3-minute review of chapter 2 there, these last 3 minutes. Just trying to set off neurons in your brain here to say, yeah, I real quickly, I remember him talking about that, but now I need to spend time studying. Just listening to me talk for a few minutes here is not enough. Got to put it into practice. Question? Cosine of 1 over x. That, yeah, that has infinite oscillations. It's not continuous at x equals 0. Yeah. Unless you multiply by x and made it piecewise, then your squeeze theorem could make it go to 0 as x goes to 0.